Hey everyone, we are looking at volumes. So when we did those areas, I had mentioned the sample rectangle thing, and the biggest reason for it actually is going to come back while we're doing this volume stuff. Okay, so say we have the square root of x, which is shown in this graph, from 0 to 9. And we're going to take this guy, and this is going to sound a little bit weird, but we're going to take this guy and we are going to rotate this thing, like this region from 0 to 9, like pretend that's like a solid block or a solid triangle-ish region. We're going to rotate it around the x-axis, creating a three-dimensional solid. And the question is, what's the volume of that solid? Like if you can picture it, I'm not even going to try to draw it, to be honest, but if you have this curved shape and you spin it around, the shape you would get would be kind of like a gumdrop or, I don't know, a bullet, but I don't like bullets. So here's the key thing though. We are never even going to try to draw the actual shapes of these things. What we're going to do instead is draw that sample rectangle. And the sample rectangles are always going to be perpendicular to the axis of rotation. I'm rotating around the x-axis, so I draw a perpendicular, like karate chop, perpendicular to it. So I have this little sample rectangle right here. That little, I just drew it in green. Okay, so if I just take this guy right here and I spin it around the x-axis and only that little rectangle, I get something that I can draw, sort of. I get basically since this is a very thin rectangle, I get a very thin disc or a cylinder essentially. So I have this disc and really it's a cylinder, a very short cylinder. I know usually you see a cylinder like this. So in this case it's like that, but it's just sideways and really not very thick. We know that the volume of a cylinder is pi times the radius squared times the height. Or another way to look at this is going to come back later, is that pi r squared, that's the area of the shape times how thick it is. So area times thickness is actually our general recipe. So no matter how weird things get, and trust me, they're going to get weird, this is really what it's about. The area times the thickness. So if I look at this guy, I know I happen to draw this where it's like I went over at x equals 4, so y is 2. But really, this is anywhere along this whole entire strip. So when I look at that red disk, though, it's still just pi r squared times h. So the radius right there, my radius is the y value. I know in this case it happens to be 2, but out here it's 3, down here it's 1. It can be anything along, between 0 and 3. So the radius is the y value. The thickness, the skinny dimension of this guy, it's some tiny change in x. This is that same sample rectangle, like we did with the areas. So it's dx for the thickness. So the volume of this little slice, this kind of sample slice created by the sample rectangle, is pi r squared h, which is pi, the radius is y, and then square it, and then the h is dx. Our h's are always going to be dx or dy, by the way. We'll come back, we'll see dy later. Okay, so the dx is the boss. And so in order to find our whole volume, so if you imagine if I drew in a whole bunch of sample rectangles, and I could have all these little sample slices, and I could add them all up. Oh wait, we've done that before. So to get our whole volume, we sum the slices. If you imagine, like you could have a stack of coins that were, if we turn it sideways, it would make this like stack of coins, and you're adding up all the coins to get the whole volume. Those coins are infinitely thin, the dx, remember, because we're talking about this perfect thing, not an approximation. This isn't like a Riemann sum sort of thing. We're going to use calculus to get it exact. So the dx is in charge, and it tells me that, well, my pi is still going to be there, but it tells me that my bounds are what the x is doing. So our x is going 0 to 9. And then y is equal to the square root of x. So I have root x squared, and I had to switch it to in terms of x because the dx says I need to have all x's. and then dx. This is awfully convenient, having the square root of x getting squared. So I have just the x. I'm going to pull my pi to the front just to get it out of my way a little bit. So I have x dx for my volume. So to get my whole volume, I just do our normal integral thing. So pi times 1/2 x squared. I started to write a pi. Happy Pi Day. It's Pi Day today. I'm making the video on Pi Day. And look, it's pi. So 1/2 x squared, and then from 0 to 9. Remember when you're doing that fundamental theorem of calculus, aka you're integrating with the, with the bounds, and your notation, you want that vertical bar at the end with your bounds. And then we can plug in our upper bound. So I have pi times 1/2 times 9 squared. I'm going to go ahead and write the minus part, because if, say this was just 1 to 9, obviously you'd have something to subtract off. So pi times 1/2 times 0 squared. So we have 81 pi over 2. Remember, it's totally fine to stop here at this point. You can stop here because once you're at this point, it's an arithmetic thing, not a calculus thing. So we get 81 pi over 2. So that's the exact volume of that kind of funky little gumdrop region. So this is our very first example, and from here it's going to get weirder. So stay tuned.